Okay, so PNR is more general than PNN because this R you can change it from 1, 2, 3 up to N. Okay, even you can define what is PN0 as well. But let's say PNR, we try to get it. So it turns out that we claim that, okay, this is my claim, that it is equal to N times N minus 1 times N minus 2 times many terms. But altogether, there are going to be R terms. Is that okay? So PNR is equal to this one, N times N minus 1 times N minus 2. And altogether, you make this multiplication up to R terms. Okay, if this is R terms, what is the last one? If there is just one term, you have N, right? If you have two terms, you have N minus 1. And if you have three times N minus 2, so R terms is N minus R, and then plus 1. Very good, okay? So it is N minus R, but you need to add back 1, okay? Is that okay? This is it. Okay, how do you prove this? The proof is very simple. This is by rule of product. Okay, so you are going to select R items and then arrange it. Make yourself very lazy. You make this selection and arrangement during R days, on R different days. So on each day, you just select one thing and then put it into the correct slot. So on the first day, you have N items to choose and to put it into the first slot, so there are N choice. On the second day, you have N minus 1 items left, and then you want to put it into the second slot. So you have N minus 1 choice, and so on and so forth. So when you repeat this process up to R days, so you have R terms here, then you are done, because we are only selecting R items altogether. Is that okay? So this is rule of product. So every counting things can be, you can after doing some analysis, it goes back always to rule of sum and rule of product. And most probably, sometimes you will need rule of difference, but that's it. Is that okay? Good. So this is the formula for PNR. So if we have a formula for PNR, you have a formula for PNN. Now you have a formula for CNR as well. So what is CNR? If you look at it, this is the relationship that you can find CNR with respect to PNR and PRR. So CNR is equal to what? It's equal to PNR divided by PRR. Is that okay? Is that okay? So this is equal to, you have N times N minus 1 up to N minus R plus 1 divided by PRR is R factorial. Okay, so that's it. Okay, so let me introduce a new notation for you, okay, so that we can make this formula easier to memorize. So first of all, what is NR? N to the power R. N to the power R is equal to N times N times N. There are terms. Is that okay? Okay. Now I'm going to define something like N to the power R, but I have a bar here. Bar here means it looks very, very close to N to the power R, except that not each term is N, but each term is minus 1 from the previous one. So it is equal to N times N minus 1 times N minus 2, altogether R terms. Is that okay? So we call this the falling function. It falls. Okay, and then we can also define something like, so this is just for notation. Okay, so we can define something like N to the power R, but this time there is a bar over here. So we call it a rising function. So we're rising. So you can guess this is going to be, you start from N, But then each term is plus 1 of the previous one. So n plus 1, n plus 2, and so on and so forth. And then there are going to be r terms. Is that okay? So this is the rising function. Okay, now using this notation, this one will be equal to, it is equal to n to the power r falling divided by r to the power r falling. Okay, so this is the CNR. Okay, you have n falling for r terms, and then divided by r falling for r terms. Is that okay? Okay, so this is just a notation, but this will be useful. Okay, when we later study a binomial coefficient. So this is something that I want to tell you. Okay. Okay, so we have learned so many things. So let's try to make some application. So the first one, so exercise 1. So you have 100 people, and then they ran into a competition, and then one of them will get the first prize, and then one of them will get the second prize. Okay, and all the remaining, they do not have any prize. Let's say there is a third one. Okay, let's say there are 3 persons, so there is a third one. There is a third prize. Okay, so how many different outcomes we can have? So how many? So first of all, is it a permutation problem or is it a combination problem? So with 100 people and they ran into a competition, someone will get the first prize, some other person will get the second, and then some other person will get the third prize. So how many different outcomes are possible? How many? So is it a permutation problem or is it a combination problem? Permutation, very good. So it is a permutation problem because the ordering matters, right? And then very simple. So this is equal to P103, right? Or you don't need to memorize the formula. You can derive it by yourself. So how do we get the results? So there are 100 ways to select the first person. And after that, there are 99 ways to select the second person. And then there are 98 ways to select the third person. And that's it. So this is the answer. Is that okay? Good. How about this one? Now this is difficult. Okay. Okay. This time we have n people. So n in general, n people. And then they want to stand in a ring. Stand around the circle. Okay. They want to stand around the circle, and then what? And then what we care is, for each person, what we care is who is standing on the left-hand side and who is standing on the right-hand side. And then we want to ask how many different ways are there. So let me tell you. So for instance, when n is equal to 3, then we can have 1, 2, 3. So this is one way. And then 1, 3, 2. This is another way. Is that okay? And there is no other different ways. Okay. Even if you rotate it a little bit, then we still consider the same way, because for each person, so if you rotate it by 90 degrees or whatever, for 1, the left-hand side is still 2, the right-hand side is 3. For 2, the left-hand side is 3, the right-hand side is 1, and for 3, the left-hand side is 1, the right-hand side is 2. Is that okay? So for every person, the left-right relationship doesn't change, so we will consider them as the same arrangement. Okay? So what I mean is that this one is considered the same as you have a 1 here, you have a 2 here, you have a 3 here. Okay? So these two are the same. So is that okay? Good. So here, we want to ask, how many different ways can we form by n people standing in a ring where rotation does not matter? But then these two are different, you see? Because for these two, the left-hand side of 1 is different. The left-hand side here is 3, the left-hand side is 2. Is that okay? So let's say they are facing into the center. How many ways are there? Okay, so for 3 person, we know that there are 2 ways, right? For 2 person, how many ways? So for 2, very good. For 2 person, 1 way. For 3 person, 2 ways. For 4 person, wow, difficult. Okay. If you are calculating very quickly, for 4 person, there should be 6 ways. Okay. Anyone? Anyone? So this is this is an arrangement problem. Yeah, ordering matters. Okay, I'll tell you the solution, and perhaps you can think about why this is true. So this solution, you can guess actually. If you don't have any idea how to solve this problem, you can draw examples. You can start by observing what are the small values for n. So let me tell you. Okay, so first of all, let me tell you. See if you can guess. Okay, I didn't tell you the formula yet. N, and then this is the number of ways. Okay. So when n is 1, there is just 1 way. So for n is 2, there's just 1 way. For n is 3, there are going to be 2 ways. Okay, for n is 4, there are going to be 6 ways. For n there's 5, I know the formula, so I can calculate this very quickly. So there are 24 ways. So for 6, there are 120 ways. For 7, there are going to be 720 ways. Okay. So for n, so in general for n, how many ways are there? Okay, good. That's a good guess. Okay. So you can guess it that for n, it is n minus 1 factorial. Okay, this is a guess only. But how do you make your guess true? Okay, how do you show that your guess is really the correct answer? It turns out that this is the correct answer. So how can you show? Any idea? Excellent. Very good. Excellent. Whenever you have a formula, and that depends on n, the first thing that you should try is mathematical induction. Because what? Okay, mathematical induction is something that is very good because it relates to very similar cases. One is about n minus 1 people, and one is about n people, right? Okay, so if you have conjecture about n minus 1 people, and then you have the formula, maybe it is very easy to deduce the formula for n people. Is that okay? So let's try mathematical induction. Okay, so the base cases, you can set 1 as the base case or 1 and 2 as the base case, whatever. So you can set these two both as the basis case. Okay, okay. And suppose that, okay, so if you use MI, mathematical induction, suppose that for n person, the number of arrangement is really n minus 1 factorial. And now, if you have n plus 1 person, then how do I get this number? And why is it true? So the idea is that, okay, so there are n plus 1 person, right? So they are the first n person. So these are the first n person, and then you have a new person that you want to add. So this is the new person that you want to add. Okay, this is the n plus 1 person. Is that okay? So you want to add it here. So how do you add it? So you can ask, okay, so this is, let's say this is a bully, okay, a big one, okay. You n guys, you make the arrangement first, and then I will enter. I will decide where I'm going to stand later. Is that okay? Is that okay? So to make an arrangement for n plus 1 person, it is easy. So all these n people, they make an arrangement first. And then I will step in. I'm the fattest one. Okay, I will step in at the last moment. Okay, so for each different arrangement of this n person and different way that I step in, it will create a different arrangement for n plus 1 people. Does that make sense? Right? Right? Yeah, because you can think of it. Let's say there are n persons here. So there are two different n persons arrangement. So this is just another n person arrangement. If I step in the same position or whatever, these two are always different because they cannot be the same. Because if I pick this out, if they are the same, then I pick this out, they should still be the same. But now they are not the same, so they cannot be the same. Is that okay? So if you start with two different arrangement of n people, then you must have a different arrangement for n plus 1 person afterwards. This is my claim. Is that okay? And similarly, if you have the same n person arrangement, but let's say these two are the same n person arrangement, but if I step in at different position, then it should give me a different n plus 1 arrangement. Is that okay? Okay? So just by counting the number of ways that we first form n people arrangement and then step in, it will be the same as we count n plus 1 arrangement. Okay, good. So we have this idea. Okay, so there are how many? So there are n minus 1 factorial ways for n people to arrange. Is that okay? And then how many different ways that I can step in? I can step in here, 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 right? How many ways are there? N ways, n. So there are n person here already. Okay, so there are n gaps. So there are n ways. So in that case, mathematical induction tells us that the number of ways that we have n plus 1 arrangement must be equal to n times this number. And n times n minus 1 factorial is exactly equal to n factorial. Is that okay? So this is the first way that we prove. Okay. So the good thing about mathematical induction is that if you have a formula and you believe that it is correct, you can easily verify it, check it. But it is not always working because maybe your formula is wrong. Okay, so it doesn't work. Or maybe after you write down so many times, you don't have any conclusion, you don't have any formula, then you cannot use mathematical induction. Okay? Good. But then, for this problem, there are still other ways to reason why this is n minus 1 factorial. Okay, so there are two ways. There are two ways. One is the first way that I like, this is what I always try to memorize by myself, is this one. We are arranging n people. Okay, so there must be a position for 1. 1 must be inside. And then to get a particular arrangement, what I need to do is I determine who is sitting or who is standing on the next position of 1 and who is standing in the next position of 1 and so on and so forth until the end. Is that okay? If you do so, then you get a particular arrangement. Is that okay? So when person 1 is fixed, so we fix the position for 1, then there are n minus 1 choice for this person. There are n minus 2 choice for this person. And so on and so forth. There is 1 choice for this person. So altogether, there are n minus 1 factorial choice for this circle. So what I'm actually doing is, you imagine that there is a scissor, or there is a knife, okay, a big knife. You cut the person 1 here, cut it, kill it. After you kill this person, then you break the loop. You break this circle into a line, make it into a line. And then this becomes an arrangement of n minus 1 person on a line. And there are n minus 1 factorial. Is that okay? Is that okay? Okay, so this is one way that I like to memorize. Okay, you can choose whichever way you like to memorize things, but this is what I use to memorize this. Now another one is, okay, another one is also interesting. We are going to use another technique called rule of, so we have rule of sum, rule of product, rule of difference. Difference comes from subtraction, right? And there is one, rule of division, of rule of quotient, okay. So we are going to divide things. Okay, so what we are going to do is, imagine that there are n fixed positions. So this is position 1, position 2, position 3, position 4, position 5, position 6, position 7, and so on and so forth up to position n. Position 1, position 2, position 3, up to position n. Is that okay? And there are n people. So there are n people that we are going to sit them here. So without any restriction, how many ways are there for these people to sit into these n fixed positions? How many ways are there? So let's say this is the position that faces north, this is the position that faces south, and so on and so forth. So each position is different. So in that sense, there should be what? There should be n factorial ways to arrange this n person into these n seats. Is that okay? If you are okay with this, could you please raise your hand? Excellent. Okay, excellent. But now in our question, we have added restriction. The restriction is that if we can rotate and obtain the same configuration, the same way, then we consider the two arrangements to be the same. So for instance, if we sit 1, 2, 3, 4, 5, 6, 7, 8 up to n here, or if we sit 1, 2, 3, 4, 5, 6, 7, 8, n minus 1, n here, we are considering them the same arrangement because one can be obtained from the other by rotation. Is that okay? So here, this n factorial is over counting. We are counting things again and again and again. Okay. How is the overcounting? How are things overcounted? For a certain configuration, it is counted n times rather than counting one time. Do you understand my point? You fix a particular configuration. Let's say 1 sits here, 2 sits here, 3 sits here, and n sits here. This is one particular way of seating this n person. But then, without any restriction, we will count this here as a different one. 1, 2, 3, 4, n minus 1, n. We will count this as a different arrangement. And we will also count 1, 2, 3, n minus 2, n minus 1, n. So this is, we will count this as a different arrangement. We will count this as a different arrangement. Am I correct? Each arrangement is counted n times, exactly n times. Overcounting it by n times. Each arrangement is overcounting by n times. Okay? So the actual number of arrangement will be equal to what? Will not be equal to this n factorial. This n factorial is overcounted. So we should divide this by n. Is that okay? Okay. Now, to understand why this is true, we will need to show that, we need to show what? Need to show for each possible answer, so this is a particular answer, answer 1, arrangement 1, each possible answer, answer 2. So let's say we don't know how many answers are there. So let's say this is answer J, okay? For each possible answer, it is overcounted by n times. The n times counted, n times counted, n times counted. And all these things, they do not overlap. Okay? If they do not overlap, then we know how many answers are there because we know what? We know what we know. We know that the total of all possible arrangement is n factorial. If the total of arrangement is n factorial and each group has exactly n of them and they do not overlap, okay, we need them to not overlap. So these are n things, these are n things, these are n things. Each one of them corresponds to a different answer, then in that case, we can use the division method, the rule of quotient, n factorial divided by n, and then we get the answer. Is that okay? But this needs to be carefully done. You need to believe why it is true, to understand why it is true. So sometimes we will make mistake here. So that's why this is a correct proof, but I do not try to memorize this as my way of reasoning. So what I want to reason it, to memorize is to cut it at 1, okay, and then make it a line. This will be simple. Okay. Okay, so it's about time. So let's take a 10-minute break, and then we come back with more examples. Okay.